Huge title. Exponential growth and decay. That's right. That's what this is all like, the encompassing umbrella. And we're going to focus on setting up equations that kind of deal with half-life and doubling time. These are usually the only types of equations that are set up with these types of exponents, but it's very possible to do other types of exponential growth and decay this way. So we're used to seeing a formula for exponential growth and decay. The most basic parent function of it would be y is equal to a times b to the power of x. This is like the most basic version of an exponential function. A is your initial value. Looks like one word there. And b is your growth or decay rate. Okay? And then x is whatever the exponent is. Usually, we're going to say it's the exponent. And usually in these circumstances, it has to deal with time, most likely. Okay? I.e. time. It tends to be time in this case. Now, we can break this formula down a little more. If I want to split it into growth and decay, let's say, what's a good color? Growth we'll put as green, decay is red. Does that make sense, kind of, for colors? Sure. If we're going to do decay, we got y is equal to a, and then in here you end up with 1 representing 100% of whatever you started with, minus your decay rate, so your percentage, we'll say. Usually it's written as a percentage. Could be written as something else the odd time. That's for decay rate. Okay, decay. And then for your growth, wait, I said growth was green, right? Yeah, growth would be green. It's going to be same idea, 1 representing 100% plus the percentage to the power of x. And this is usually your growth rate. This is usually your growth rate formula. Okay, so we add the percentage, we subtract it. Half-life and double time. Okay, half-life is referring to decay, how long it takes something to go by half. A half-life formula is usually written like this. Y is equal to A. Because we're using the word half-life, we already know what our base of our power is going to be. It's a half or 50%, however you want to look at it. But what ends up happening is our time is then divided by, and you can really use any variable you want here. We're going to use it as the variable, maybe k, n. Have we used n yet? No, I haven't used that. And we're going to say that n represents time to pass for half-life. Time to pass for, actually no, time to pass for event to happen. That way we can use it for both. Event to happen. Now, I want to make sure this makes sense to you. Okay, and what we'll do is we'll build an entire, we'll build a kind of question off this. And for doubling, doubling is a growth. Y is equal to A is the initial value. Doubling represents 2. We're growing by 100%. And same idea, x is actually, again, divided by n. So the exponent ends up being the same. It's not like we multiply by that, okay? So that's the same n as in the decay rate. So if they're given a question where you say, oh, we have, we'll call this a half-life question. I know I've just kind of given it away. This is a half-life question, for example. We start with 100 items. Doesn't matter what they are. It has a half-life, and the half-life is, so we're calling it the HL, the half-life is every 10 days. Okay? How do we set up this formula? That's what we need to do. How do we set this up? Okay, well, our y is equal to, our a value is the 100. Because it's half-life, our base is going to be a half or 50%. And the only variable left here is going to be x, and it's going to be divided by 10. So in other words, for this event to happen, 10 days have to pass. So let's say it's the half-life of some, they usually say bacteria. Let's say it's the half-life of my money because I spend it so fast. My half-life of my money, every 10 days, my money gets cut in half because I have no control. So what that means here is after 1 day, the half-life hasn't occurred yet. It takes a total of 10 days for the total event to happen. So what that means is when I put 10 in here, you'll notice 10 divided by 10 is equal to 1, okay? And anything to the power of 1 is itself. So we're now doing 100 times a half, and 100 times a half is 50. Essentially half the money I originally started with. So that's what I mean by how long for the event to happen. Okay, so that's what's really important there. If the half-life was every single day, well, divided by 1 isn't really hard to set up. We don't even have to divide by 1. If the half-life was every half day, we'd actually divide by 0.5, and it'd be even faster than a day. So it's a really important value to put in here. And same with doubling time. If it was doubling time every 10 days, the only thing that would change is the base here. This still number, how long it would take for the event to happen, would stay the exact same. Okay.